Graphical games. In this chapter, we examine the representational and the algorithmic aspects of a class of graph theoretical models for multiplayer games. Known broadly as graphical games, these models specify restrictions on the direct payoff influences among the player population. In addition to a number of nice computational properties, these models have close connections to well-studied graphical models for probabilistic inference in machine learning and statistics. Introduction. Representing multiplayer games with large player populations in the normal form is undesirable for both practical and conceptual reasons. On the practical side, the number of parameters that must be specified grow exponentially with the size of the population. On the conceptual side, the normal form may fail to capture structure that is present in the strategic interaction, which can add understanding of the game and computation of its equilibria. For this reason, there have been many proposals for parametric multiplayer game representations that are more succinct than the normal form and attempt to model naturally arising structural properties. Examples include the congestion and the potential games and related models. Graphical games are a representation of multiplayer games meant to capture and exploit locality or sparsity of direct influences. They are most appropriate for large population games in which the payoffs of each player are determined by the actions of only a small subpopulation. As such, they form a natural counterpart to earlier parametric models, whereas congestion games and related models implicitly assume a large number of weak influences on each player. Graphical games are suitable when there is a small number of strong influences. Graphical games adopt a simple graph theoretical model. A graphical game is described at the first level by an undirected graph G in which players are identified with vertices. The semantics of the graph are that a player of vertex I has payoffs that are entirely specified by the actions of I and those of its neighbor set in G. Thus, G alone may already specify strong qualitative constraints or structure over the direct strategic influences in the game. To fully describe a graphical game, we must additionally specify the numerical payoff functions to each player, but now the payoff to player I is a function only of the actions of I and its neighbors rather than the actions of the entire population. In the many natural settings where such local neighborhoods are much smaller than the overall population size, the benefits of this parametric specification over the normal form are already considerable. But several years of research on graphical games has demonstrated that the advantages of this model extend well beyond simple parsimony. Rather, they are computational, structural, and interdisciplinary as well. We now overview each of these in turn. Computational. Theoretical computer science has repeatedly established that strong but natural occurring constraints on optimization and other problems can be exploited algorithmically, and game theory is no exception. Graphical games provide a rich language in which to state and explore the computational benefits of various restrictions on the interactions in a large population game. As we shall see, one fruitful line of research has investigated the topological restrictions on the underlying graph G that yield efficient algorithms for various equilibrium computations. Structural. In addition to algorithmic insights, graphical games also provide a powerful framework in which to examine the relationships between the network structure and the strategic outcomes. Of particular interest is whether and when the local interactions specified by the graph G alone, i.e. the topology of G regardless of the numerical specifications of the payoffs, imply non-trivial structural properties of equilibria. We will examine an instance of this phenomena in some detail. Interdisciplinary. Part of the original motivation for graphical games came from earlier models familiar to the machine learning, AI, and the statistic communities, collectively known as graphical models for probabilistic inference, which include Bayesian networks, Markov networks, and their variants. Broadly speaking, both graphical models for inference and graphical games represent complex interactions between a large number of variables, random variables in one case, and actions of players in a game in the other, by a graph combined with the numerical specification of the interaction details. In probabilistic inference, the interactions are stochastic, whereas in graphical games, they are strategic best response. As we shall discuss, the connections to probabilistic inference have led to a number of algorithmic and representational benefits for graphical games. In this chapter, we will overview graphical games and the research on them to date. We will center our discussion around two main technical results that will be examined in some detail and are chosen to illustrate the computational, structural, and interdisciplinary benefits discussed above. These two case studies will also serve as natural vehicles to survey the broader body of literature on graphical games. The first problem we shall examine is the computation of Nash equilibria in graphical games in which the underlying graph G is a tree or certain generalization of trees. Here we will discuss a natural two-pass algorithm for computing Nash equilibria, requiring only the local exchange of conditional equilibria information over the edges of G. This algorithm comes in two variations. One that runs in time polynomial in the representation size of the graphical game and computes a compact representation of approximations of all Nash equilibria, and another that runs in exponential time, but computes a compact representation of all Nash equilibria exactly. We will discuss a number of generalizations of this algorithm, including one known as Nash prop, which has close ties to the well-known belief propagation algorithm in probabilistic inference. Together, these algorithms provide examples of the algorithmic exploitation of structural restrictions on the graph. The second problem we should examine is the representation and the computation of the correlated equilibria of a graphical game. Here we will see that there is a satisfying and natural connection between graphical games and the probabilistic models known as Markov networks, which can succinctly represent high-dimensional multivariate probabilistic distributions. More specifically, we shall show that any graphical game with graph G can have all of its correlated equilibria up to payoff equivalence represented by a Markov network with the same network structure. If we adopt the common view of correlated equilibria as permitting shared or public randomization, the sources of the correlations, whereas Nash equilibria permit only private randomization or mixed strategies, this result implies that the shared randomization can actually be distributed locally through the graph, and that distant parties need not be directly correlated. From the rich tools developed for independence analysis in Markov networks, it also provides a compact representation of a large number of independent relationships between player actions that may be assumed as correlated equilibrium. The result thus provides a good example of a direct connection between graph structure and equilibrium properties, as well as establishing further ties to probabilistic inference. We shall also discuss the algorithmic benefits of this result. After studying these two problems in some detail, we will briefly overview recent research incorporating network structure into other game theoretic and economic settings, such as exchange economies, Arrow-Debreu, Fisher, and related models. Again, the emphasis will be on computational aspects of these models and on the relationship between graph structure and equilibrium properties.